For the past several years, our experience with artificial intelligence has been almost entirely cloud-based. When you interact with a large language model or use an AI image generator, your request is sent to a massive data center located hundreds or even thousands of miles away. There, powerful clusters of GPUs process your data and send the result back to your device. This is cloud AI. While it has allowed us to access immense computing power, we are now hitting a fundamental limit caused by three specific factors: latency, privacy, and bandwidth. As AI moves from being a novelty to an essential tool integrated into our operating systems, waiting for a round trip to the server is no longer acceptable. Think about real-time AI tasks, instant voice translation, gaze correction during a video call, or live cybersecurity scanning. If every single mouse movement or spoken word has to be uploaded to the cloud, analyzed, and sent back, the experience becomes laggy and broken. This is known as the latency gap. Furthermore, we are facing the issue of data gravity. As we generate more high-resolution data locally, it becomes physically and financially impossible to upload everything to the cloud for processing. This is where Edge AI comes in. The Edge refers to the local device in your hand or on your desk. Edge AI is the practice of running AI models directly on your local hardware. By moving the processing to the device, we ensure that sensitive personal data never leaves the machine, providing a level of privacy that the cloud can never guarantee. However, running modern AI locally presents a massive hardware challenge. To understand this, we have to look at the mathematical nature of AI. Unlike traditional software that follows a linear logic, if this then that, AI models are built on neural networks. These networks consist of millions or even billions of weights arranged in layers. When you give an AI an input, it has to perform a massive amount of matrix multiplications, thousands of simple calculations happening simultaneously across these layers. For decades, our computers relied on the CPU, Central Processing Unit. A CPU is a general-purpose processor designed for serial processing. It has a few very powerful cores that are extremely fast at doing one complex task after another. While a CPU can technically run an AI model, it is incredibly inefficient at it. It's like using a world-class surgeon to move thousands of tiny bricks. He can do it, but it's a waste of his specialized skills and takes forever. We also have the GPU, Graphics Processing Unit. The GPU was a major breakthrough for AI because it is designed for parallel processing. It has thousands of smaller cores that can do many simple things at once, which is perfect for the matrix math that AI requires. However, the GPU has a major flaw: power efficiency. A GPU is designed for high-performance rendering. It requires massive amounts of wattage and generates significant heat. If you run a large AI model on a laptop GPU, your battery will drain in an hour, and the fans will spin at maximum speed. This technical gap, the need for a processor that is as parallel as a GPU but as power efficient as a mobile chip, led to the birth of the NPU, or Neural Processing Unit. The NPU is a specialized piece of silicon architecturally stripped down to do only one thing: accelerate the mathematical tensors that power AI. It is not just an upgrade, it is a fundamental redesign of how a computer thinks locally. In this episode, we've identified why the shift to the edge is necessary, and why our legacy processors are no longer enough. The stage is now set for the NPU to take over as the new heart of the AI PC. To understand why the NPU is a game changer, we have to look past the marketing terms and dive into the actual architecture of the silicon. For decades, computer science has been governed by the von Neumann architecture, where the processor and the memory are separate. In a standard CPU, every time a calculation is made, data must travel from the memory to the processor and back. This data movement is actually what consumes the most power and causes the most heat. In the world of AI, where we deal with billions of parameters, this traditional cycle becomes a massive energy drain. This brings us to the core design of the NPU, Neural Processing Unit. While a CPU is built for flexibility, able to handle any unpredictable logic or complex branch instructions, the NPU is built for determinism. AI workloads primarily consist of deep learning tasks, which rely on a mathematical operation called multiply-accumulate (MAC). Imagine a massive grid where you multiply two numbers and add the result to a running total, billions of times over. The NPU solves the power problem by using a dedicated array of hundreds or thousands of Mac units hardware wired to work in parallel. But the real secret sauce of the NPU is its local memory architecture. Unlike a CPU that relies heavily on external cache or system RAM, an NPU often has its own small, ultra-fast memory located right next to the processing units. This minimizes the distance data has to travel, effectively bypassing the von Neumann bottleneck. This is why an NPU can perform trillions of operations per second, or TOPS, while using less power than a standard light bulb. Another critical architectural difference is precision. In traditional computing, we often use 32-bit or 64-bit floating point numbers for extreme accuracy. However, neural networks are remarkably resilient. They don't need that level of precision to be effective. The NPU is optimized for quantization, which is the process of converting high-precision numbers into 8-bit or 16-bit integers, int8, int16. By working with smaller data types, the NPU can process 4 to 8 times more data in the same amount of time and space. It's like switching from a heavy, slow truck carrying a single massive block to a fleet of fast, light motorcycles carrying smaller boxes. The throughput increases exponentially while the fuel consumption drops. Furthermore, the NPU features specialized hardware for activation functions and data compression. In an AI model, not every neuron fires at the same time. Many values in an AI matrix are zero. This is called sparsity. A traditional GPU might waste energy calculating those zeros, but a modern NPU has sparsity acceleration built in. It simply skips the zeros, saving even more cycles and power. This level of specialization is why the NPU is the only reason we can now run complex AI models like Llama or Stable Diffusion on a thin and light laptop without it melting through your desk. We have moved from general-purpose computing to domain-specific architecture, where the hardware is literally shaped by the math it is meant to solve. We have reached the final stage of the AI revolution, the transition from assisted computing to autonomous computing. For years, our devices were merely windows into the internet. Without a connection to a central server, your smart assistant was useless and your software was static. The introduction of the NPU changes this power dynamic forever. We are entering an era where your computer doesn't just execute your commands. It understands the context of your actions in real time, locally, and privately. The most immediate impact of the NPU-driven edge AI is the total elimination of the privacy versus utility trade-off. In the cloud era, if you wanted a powerful AI to analyze your health data, your financial records, or your private emails, you had to upload that sensitive information to a third-party server. With a dedicated NPU on your device, that data never leaves the silicon. The AI model comes to the data, rather than the data going to the AI. This creates a zero-trust AI environment where you can have world-class intelligence without sacrificing a single byte of personal privacy. But the real transformation lies in system-wide intelligence. In the past, AI was an app, something you opened, used, and closed. In the NPU era, AI becomes a background OS layer. The NPU will be constantly working at a hardware level to optimize your device. It will manage your battery by predicting which apps you'll use next. It will provide system-wide live captions and real-time translation for every video or call, regardless of the language. It will even act as a proactive security guard, using behavioral analysis to detect malware patterns that traditional antivirus software would miss, all while consuming less than 2 watts of power. As we look further ahead, the NPU will enable the rise of AI agents. These are not just chatbots. They are autonomous entities that can navigate your file system, organize your schedule, and execute complex workflows across different applications. Because the NPU handles the mathematical heavy lifting, these agents can run 24/7 without overheating your laptop. We are moving toward a world where the distinction between human input and computer output begins to blur. Your computer will become a proactive partner that anticipates your needs based on local context that only it can see. The shift to edge AI and the NPU is the final piece of the puzzle. It marks the death of the passive terminal and the birth of the intelligent machine. We no longer need to build bigger and bigger data centers to make our devices smarter. We just need to build smarter silicon. The NPU isn't just another chip on the motherboard. It is the fundamental brain of the next generation of computing. The era of cloud dependency is ending. The era of autonomous, private, and instant intelligence is here.